card trick and the mathematics behind it. Binary numbers. So every number can be expressed in binary numbers, and every number is binary. So we'll have 0 and 1. For example, 1 has 2 to the 0, so its binary would be 1. And 10 is made up of 2 to the 3rd and 2 to the 1st, which means its binary is 1, 0, 1, 0. And these are some other numbers and their binary codes. Modular arithmetic. It refers to the remainder after division. 6 divided by 2 has a remainder of 0. So its mathematical representation is 6 is congruent to 0 mod 2. And these are other numbers.
Okay, so the game is played with this set of cards. So if you can just look at it for a second, you'll notice some patterns in there. Each card starts with a power of 2. And here, let me just explain the game. So the game, there's a magician in an audience, and the audience member will pick a number between 1 and 63, but they won't tell the magician what it is. And then the magician will ask for which cards out of that set that the number will appear on, and then the magician will be able to guess the number. So how? Well, let's take the number 49. It appears on card 1, card 5, and card 6. And if you add the first numbers on each of these cards, so 32, 16, and 1, you'll notice that it equals 49. So how does that work? Well, each card represents all of the numbers that contain that binary expansion. So card 1 contains all the numbers that contain a 2 to the 0 when you expand it. And card 2 contains all the numbers that have a 2 to the 1st. So just to give an example, 3 would appear on both card 1 and card 2 because it contains a 2 to the 1st and a 2 to the 0. So these are just some explanations of the variables that we're using. A, K, N is the nth number in the kth card. So 49 is A518. So we notice a general pattern in the cards. It can be written as this, which is extremely big, so we'll break it down. So for example, if we take 49, we can plug it in and say 49 mod 2 to the 4, which is 16, is not equal to 1. You don't have a remainder of 1, so you add 1, and 49 would then go to 50 in the next column, or the next cell. So we decided to take this to another step, and yeah, so we put this on the faces of a cube, and if I can open the cube file. Well, let's just use these. I have it on the computer, but just these are a bunch of them.
Escape, is that a different file?
Yeah,
it's a
different file.
Just you need to escape.
It might be on the Mac or.
It's here, yeah, it's this one.
But why is not showing it's not working? It changed the screen, but it didn't change
For
it.
some reason it opened up in this. So I don't know.
You wanna maybe close the PowerPoint, and then reopen it.
There we go.
It's all
Oh, okay.
I think it's playing a card game with you.
Okay, okay, yeah, there we go. So, yeah. So yeah, we decided to put all these cards on the faces of a cube. And so the top, it goes like a standard dice. So the top is the first card and the bottom is the sixth. And then 2 is on the front, 3 is there, 4 is there, and then 5 is on the back. So, yeah. No, let's just do it from here.
Just at this one.
Oh.
So,
Okay, so there's a pattern. The corners of each card, if you add these two numbers, so this corner here and this one here, and that one, they equal the same number every time. So we decided to this is pattern. It's just using variables, but you have to prove that, right? So we made it into a linear system and then just substituted it in and simplified it. Now here, one of these additions is always 0 and the other one is always 2 to the k. So then you get 2 to the k equals 2. But that statement is not good. So prove that too. So no matter what, one variable will stay the same. So on the first 4 cards, 15 is the same number. But then it's 56 on the last 2 because the fourth one starts with 16, and so you can't have a 15 on there. But these are just some other patterns that we found. These are not proven yet. So
Okay, so we saw that on cards, so if columns started with the same number, they would have the same numbers throughout the whole column, like the 7, 23, 39, and 55. And then adjacent cards, sum of numbers subtracted from the next row on the same cards with the same difference or patterns throughout. So 31 plus 20 is 51 minus 15 plus 40 plus 4 will be the same thing as 47 plus 36 minus 31 plus 20.
and we have no idea why. So any questions?
Want to pass out the cubes?
Okay, yeah, you wanna?
Can you just show back the previous slide? So this is a general pattern, like what would happen with 63, 52, for example.
Well, if you add 63 and 52, you get what? 1.
Well, their difference is 11, because 15 minus 4 is 11, 31 minus 20 is
So
11,
15 minus
47.
4, yes, okay. And same thing with the 5, 6, difference is 1.
I have a question. So the original game was played with the mathematician and the audience, where they read off a number from the cards and then they read off the card numbers and then he guesses the number.
Yeah.
Is there a new game where using the cubes and a mathematician figure?
Well, the cube is kind of just putting the cards.
Okay.
So it's kind of the same thing.
Yeah, it's just taking a perspective on it.
Any other questions?
Once again, how did you, when you put them on the cube, exactly what rule did you follow?
Oh, just like a standard dice. So 1 was on the top and 6 was on the bottom, like a 6.
One, card number 1.
Yeah, and then card number 6.
Have you thought of actually reprinting like those cards, but with binary notation instead of decimal notation, and see if you see any patterns that way?
No, that's actually a really good idea.
Okay.
So let's give them another round of applause.